as a little means of introduction, I'm Cameron Rappaport. I'm a field product manager for Stationary Equipment Solutions, which essentially means the products that Chesterton puts into valves, flanges, things that don't typically move all of the time. And joining me today is Gregory Cole. Well, raise your hand, Greg. So,
right here.
Yep. Yeah, there we go. All right. Greg is a design engineer here at Chesterton, and Lucas Norton, the other guy, is also a design engineer here. And they do quite a bit of testing with us, so they're in the lab using these testing standards, so they're really the best guys to answer any questions that you guys might have about them. So, before we get into the presentation, we have a short video. What's that? Oh, you're out of focus. I think we'll figure that out. Anyway, before we get into that presentation,
there we go.
We have a quick video for you guys. That showcases the lab, so this way you can kind of start by seeing what these tests look like as they're being performed. So the valve test facility is open air because it does contain some flammable chemicals, some high pressures. Starting out with 624 testing, so the installation of the valves. Luke and Greg, if you guys have any comments on this, since you guys are the ones who do these things.
Yes, right now we're looking at our forged valve setup. We can run 3 forged valves simultaneously.
Actuating, counting the revolutions, so we'll discover how many of those we do, the importance of them.
What that really does, it just limits our stroke length. So we don't want to backseat the valve completely. We don't want to fully seat the valve. We run into issues of damaging the valve if that's the case.
All right.
.622 test rigs. Those are packing specific. You can see that they're all insulated at this time because it is a thermal test as well as an ambient temperature test.
And what you're seeing here is just kind of, before we test any valve, we do a quality check. Make sure we're testing the correct valve, that the valve meets the design standards that were provided by a given OEM. We don't want to be testing a valve that we shouldn't be testing in the first place, so we always do a quality check before any of the valves reach our test stands.
So we do borated water testing, although it's not something we're going to be covering in the scope of this webcast. That was something that we actually designed because of a specific issue our customers were having with borated water. See, the TA Luft testing looks a little bit different. That rig, they're not using that handheld sniffer, so we'll get into exactly what's going on right there. All right, hopefully that was informative for you guys. So before we get into these test standards, I'd like to just talk for a second about how these came about, because I always like to have a little bit of context. So basically, at least in the United States, these are all driven by the Clean Air Act, which came out in the 1970s, in 1970, and then as that started to be enforced in the 80s and the 90s, the EPA started going after end users, started going after places like refineries, chemical plants, getting them to institute LDAR, which is your leak detection and repair programs. And then if they were underreporting their emissions, what would happen is they'd find them and it would result in a consent decree, which is basically a legal agreement. It's a lot like a settlement in a lawsuit. So these things rarely actually go to court. What happens, the EPA sues the user, they find them, and then they, without going to court, they agree to this document. And a lot of them look pretty similar, especially when you get into the LDAR portions. And those are all public documents. You can find them online. And generally how the evolution of testing went is it started with end users. So they knew they had to comply with the Clean Air Act, and they needed a way to figure out if their valves were going to leak and to test different manufacturers to see which had higher quality valves. So they ended up developing their own test standards. So specifically, Shell and Chevron were the most widely used, and those actually formed the basis for later. OEMs also developed their own standards. And anytime this happens, you end up comparing kind of apples to oranges. You have one test that might use one media, a different test uses different media, and it's hard to actually tell who might make a more reliable valve in these emission services. So everything was unified, or mostly unified, by these three main bodies. So you have the API, ISO, and then TA Luft, which isn't a regulating body, but we'll get into that when I actually talk about that particular standard. And these are getting more and more important because there's a lot more environmental awareness through the public, through the media, and that's putting a lot of pressure, and legislatures are feeling that. So they're actually going after all these emitters of volatile organic compounds or greenhouse gases. So this is all getting a lot stricter. Great, Lucas, if you want to talk a little bit about API 622, our first standard.
Yes, API 622 is a packing standard, or packing test standard, specifically for fugitive emissions. Anytime you're working with any standard, it's important that you do a little bit of research and are positive that you have the most current edition of the standard. Always check that you're using the current edition. If you're using an outdated version of the standard, you're doing yourself a complete disservice, and it's not going to be the test that you want it to be. So because API 622 is a packing standard, it tests three different areas of the packing. It's emissions, or its leak rate, its resistance to corrosion, and its general materials test of what's it made of, what its density is, material nature of the test. So the test rig is designed to mimic a 4-inch, 300-pound class valve. This basically, this ensures that every packing that goes into this valve is under the same conditions as the previous test. It's not going into different valves that might have different stuffing boxes. It's always the exact same, and it's a specific test rig defined by the standard. So what actually API has started to do is link up all of their standards. So API 624, which we're going to get into shortly, is a valve standard, and that actually requires that any packing that is in an API 624 valve has actually already passed API 622. So the API 622 is designed to operate over about 6 days. In those 5 days, we're going to experience 1,500 cycles. That's going to be 300 cycles a day, 150 at ambient temperature, and then we raise the temperature up to 500 degrees Fahrenheit and do another 150 cycles. We let it cool overnight and repeat the process the next day. On the 6th day, after we've done our last thermal cycle, we do 10 more cycles, And the reason for that is to kind of, now we've stressed out the packing as much as we possibly can, and we want to just give that last check to see, does it still seal even after all of that stress. The gas that we use for testing 622 is methane. As a result, we have to do the test outside in our outdoor facility. So method 21 is a standard form of determining your leak rate. It's adopted in many standards as a way to guarantee that you're using the right equipment, your equipment is calibrated, and you're testing to a uniform method. It just keeps everybody, just the whole purpose of the standards is to keep everybody consistent no matter where you're doing this. It's a sniffer method that creates sort of a nest around the stem and sniffs all around the stem. You average out your readings. It's rather standard, efficient method, the most common method of leak detection. API 622 always measures leakage at a static position, meaning that the stem is not moving when we're taking our leakage measurements. And it's not a pass-fail test. It's designed to just measure the performance of your valve. The test does have a stopping point at 500 parts per million, which is considered low emissions. At this point, below 500 parts per million is low emissions, but the test doesn't have a pass-fail criteria. It's simply stating this many cycles, this many thermal cycles is when my valve exceeded 500 ppm, or it never does.
Yeah, I know that's probably one of the more commonly asked questions. Is people will say, "Oh, well, did it pass API 622?" And that's kind of a nonsense question.
Yeah, it's very common to hear, "Oh, did it pass? Did it pass?" And it's kind of based on how well you're expecting the performance to be. We have our own limitations of how we expect our products to perform, and so in that sense, we have a pass-fail criteria for ourselves, a standard that we hold ourselves to. But no, the test in itself is really just a measurement more than a pass-fail.
Yeah. Well, you will find that most people end up using 200 or 100 ppm. 100, I think, is becoming really the most common.
Yeah, 100 is becoming very common. In fact, the future of the standard will probably head in that direction, where they'll go from 500 parts per million to 100. So it also allows one retorque once you experience a leak rate over either 500 ppm or the leak rate that you're desiring to achieve. You're allowed to retorque your gland bolts, reapply the gland load, and in most instances that will bring your leak rate back down to a low emissions level, and you can continue the test.
That 500 ppm is really a safety thing, right? So methane is bad for you. It's been in the news a lot of the leak in California, and it's flammable.
Yeah. So the corrosion portion of the test is done in an alternate test rig, where we basically soak the packing and then compress it to 30,000 megapascals and let it sit while wrapped around a metal. It's very beneficial because you can change the metal. You can see how it's going to affect different stems based on what material you intend to use for your particular valve. And it's really just a time-based test. They're looking for how much pitting occurs, for how much the packing material gets stuck to the stem afterwards, and just the general conditions of the packing.
All right, so does that have a failure point, a pass-fail?
No, that's just a observational part of the test as well.
All right.
The material test gets into your actual material properties of the packing: its weight, its density, how much lubricant is in it, what its PTFE content is, if any chemicals are going to leach out of it. And those are your more typical tests. Weight loss test is done at temperature. You weigh it, bring the temperature up incrementally and weigh it again and see how much you lose. Density is just a calculation, and your lubrication concepts actually reference other ASTM standards to help you guide you through the process of determining the PTFE content of your packing. It's really just a get to know your packing portion of the test.
All right, are there any pass-fail portions of this?
Yes, the weight loss for foil graphite, for graphite foil packings is 15%. If you experience a greater than 15% weight loss at 538 degrees Celsius, that's considered a failure. And for braided packing, it's a 50% weight loss is allowable before it's considered a failure.
All right.
Or at least a stop test. The future of the industry, this standard came out in 2011, I believe, so it's been 5 years since we've been using it. We found that 100 parts per million is an achievable leak rate pretty widely across the industry, so we expect the next version of the standard to come out to reflect 100 ppm with no retorts, and that's based on the capabilities of the industry. As we continue to evolve with the technologies and the packings that we use, so will the standards in order to keep our emissions rates low. We're also considering, or the API committee is also considering, which we do take part in, is considering a 1/8 inch cross section, which is currently the 622 is only for 1/4 inch, and a rotary test rig as opposed to the rising rotating, which it is now. I think that pretty much covers 622.
Great. So yeah, Greg, if you want to talk a little bit about our next standard, which is 624.
All right, so API 624, we're currently on the first edition of the standard. Came out in 2014, so what you're seeing now is that a lot of valve manufacturers are starting to test their valves to API 624. And this is a valve-specific test. It's not just a packing test as API 622 is, but it's actually testing the entire system of the valve. For leakage criteria, you're going to be testing at the body bonnet joint and at the packing. But throughout the life of the test, you're also going to be testing the capabilities of the mechanical portions of the valve. Like I said, this is a valve-specific test. It does require a API 622 qualified packing to be installed into the valve. And this is intended for rising and rotating block valves. This isn't for rotary valves, and this isn't for control valves. So as the standards are written or will be revised, including API 600, 602, 603, and 623, those are your cast gate valves, your forged gate and globe valves, your alloy steel gate valves, and your cast globe valves. If not already, they are going to be required to be tested to API 624. So this is why you'll see a drive right now and in the future for all this to API 624 testing, because as these standards are revised, they will require 624 testing. And this test also utilizes the EPA Method 21 leak detection. So again, you have a TVA, a methane sniffer, and you go around the valve at its leakage points and you test for leakage. One important part about this test is that it's always going to be in the vertical position. This helps ensure that no matter the test location, no matter the test valve, it's always going to be in the same orientation. It's not horizontal. You can actually run into problems if the valve is oriented horizontally with side loading of the stem, specifically if you're using a globe valve, which the mass of the globe can weigh on the stem.
I just did something. Sorry, guys.
There we
That
go.
was my first time. Sorry. Yeah, so actually we have a question over here that I'd like to
Sure.
answer before we forget about it. So Sam was asking how far we'd expect the standard threshold to be 100 ppm across the industry.
I think the last I heard about the standards, they were hoping to release sometime this year. That was potentially a little bit optimistic. I would say late this year, maybe early next year, you might see a revision of API 622 coming out that we would expect to reflect a 100 ppm.
Yep. And the 100 ppm, that's actually a very well performing packing. It's there are packings out there right now which claim to be tested to API 622 that are not capable of the 100 ppm, but still qualify for an API 622 packing because they can withstand 500 ppm. But in with the current technology, for the temperatures that we're given, 100 ppm for the foreseeable future can be expected.
Great. So Sam, if you have any other questions, that wasn't clear.
Keep them coming.
Yep.
So the API 624 is going to have 310 mechanical cycles. It operates a little bit quicker than our 622. It only needs to be done in 4 days. It experiences 3 thermal cycles. So that's doing 50 cycles at ambient, coming to temperature, 50 cycles at temperature. The test temperature is 500 degrees Fahrenheit with a pressure of 600 psi. We test with methane, so again, these need to be done outdoors, and there's no retorques allowed with these tests whatsoever.
Yeah, so this is seemingly less rigorous than 622, so fewer mechanical cycles, fewer thermal cycles. Why is that? Why would you kind of decrease the standards going into the valve testing?
So, the concept is that you've already tested your packing. The packing has already been tested to API 622. It's been proven independently, standing on its own in a specifically designed test rig. What the 310 mechanical cycles for API 624 is meant to represent is an extended life cycle of a standard block valve. Most block valves aren't going to see 310 cycles. And what we find is that as you approach 310 mechanical cycles, it's not always the packing that's going to fail the test. It's a mechanical part on the valve itself. So you will have stem threads that break, you will have glands that yield, you will have other parts of the valve that will actually fail before the packing does.
All right, really interesting. It was a life of the valve test.
Yes. Yeah. So the valve is qualified in an API 624 test. So API 624 at the end of the standard actually lists a number of valves which it recommends that are tested for a given product line from a valve manufacturer. And this is because given one valve, you can qualify essentially very similar valves to this. So when you have a 3/4 inch class 800 API 602 valve, so either a gate or a globe, you can qualify the NPS 1 and smaller up to class 800. And if it's a gate valve, that would only qualify for the gate valves. If that's a globe valve, that would only be for the globe valves. For an inch and a half 800, that qualifies NPS 1 1/4 up to 2 1/2, also including all pressure classes up to 800. Now we get to the 1500. If you test a 3/4 inch 1500 pound valve, that qualifies NPS 1 and smaller, but only in the class of 1500 pound. And similarly, with the inch and a half 1500 pound valve, that qualifies an inch and a quarter up to 2 1/2 inch, again, only in the 1500 pound class. With the other valves, it's less specific to actually calling out a class and a pipe size, but for API 600, 603, and 623, you would typically test a 4-inch, a 12-inch, and a 20-inch to qualify an entire product line. But for a 4-inch that will qualify up to the 4-inch and one size larger than the 4-inch for the valve tested, and also one pressure class lower. For larger than a 4-inch, that so let's say we qualify we test a 12-inch, that's going to qualify 2 pipe sizes smaller and 1 pipe size larger for that pressure class, and also 1 pressure class lower.
All right.
In those same sizes, correct? Those same 3 sizes.
Yes.
Right.
Yep.
Yeah. So I guess the idea is basically you don't want to test every valve.
Yeah.
Right.
These can get pretty expensive.
Yep. So these tests are quite pricey. So if you were going to run every valve in your product line, the cost would add up very, very quickly. So at the end of the API 624 standard, there is a list of recommended tested valves.
All right. We'll talk about the next standard. It's from the next, actually a different body. ISO is 15848-1. So if one's important, there is a -2.
There is a -2. But for the -1 portion of this test, we're currently in the 2nd edition. The 2nd edition actually came out about mid last year, and there were significant changes. So if you're testing to, I believe it's the 2011 version, the 2015 version does have some significant updates. And this is this test procedure it's more of intended to be a universal emissions test, not specific towards the American petroleum market, as the API standards are written for, but this really covers all leaking valves in various industries throughout the world, and it's an international standard. So this standard, like I said, it's meant to be universal, so there are different portions of the test, and we can cover both block valves and control valves. Along with that, we can also cover high and low temperatures, such as cryogenic temperatures, and a standard part of the test is up to 400 degrees C, which is actually 752 Fahrenheit. So the temperatures can climb pretty quickly. And there's also high and low cycling applications. That can be broken down between control valves and block valves. For a block valve, up to 2,500 cycles in a block valve, which is really pushing the limits of most block valves. For a control valve, we're talking at the higher limits of 100,000 cycles. And there's various leakage classes. This is going to be dependent on the type of sealing being used, whether it's packing or a bellows seal, and the expectations from the customer and the capabilities of the product being used. There's also one of the biggest changes in this from going from the 1st edition to the 2nd is now there's the use of helium or methane. The previous version really only allowed for the use of helium. Now that methane is an acceptable method, this is becoming more utilized in the United States, where the EPA will really only recognize methane as a suitable test fluid. And a standard test is going to be dependent on the pressure class of the valve. So you will go to the rated pressure of that valve at the given temperature. So if your ambient test would the test would be pressurized up to the rated pressure of that valve at ambient temperature. Once you're at the test temperature, that pressure will actually decrease to the rated pressure of the valve at that temperature. And retorques are allowed in this standard. So here we go. So we have 2 different medias we can choose from, helium or methane, and what that may depend on is end user requirements, or maybe the valve manufacturer specifically wants methane over helium or helium over methane for their own reasons. For helium, there's a few different ways to measure this. What we're showing here is the volumetric leakage classes, and so we have AH through CH, and as you might be able to tell, the H stands for helium. In the methane class, again, you have classes A through C, and then you have M for methane. And the highest class you can get is the class AM, which is 50 ppm, up to Class CM, which is will actually qualify a valve up to 500 ppm.
Yeah, so people might be wondering why that you would measure these in different ways.
It's actually it has to do with the test equipment. So with methane, the EPA really is trying to steer everyone towards EPA method 21. So that's actually the method that's used in the field. So why not use the method that's used in the field to test a valve? So there's no trying to correlate different values. It's 5 or 50 ppm in a test in a lab is going to be 50 ppm out of a valve in the field. When you come to helium, most people aren't lugging a helium mass spectrometer around with them in the field. So this is really just set up for a lab environment.
Yeah. So that TVA, that handheld sniffer, can't measure helium.
Correct. And so this test, again, meant for all sorts of valves. So you can test control valves and you can test block valves. The endurance classes for a control valve, first class is CC1, which only goes up to 20,000 cycles, all the way up to CC3, which is 100,000 cycles. Again, for block valves, CO1, actually we're looking at 205 cycles. This is a little mistype here on the PowerPoint, but CO1 is 205 cycles, CO2 is up to 1,500 cycles, and CO3 is 2,500 cycles.
Yeah, so for the control valves, are those full cycles, or is that all the way on to all the way
For
off?
a control valve, it's actually, you start at the midpoint of the stroke, and it's plus or minus 10%.
Okay. So that's going to be a little bit more realistic as far as what their usage is going to be.
Yeah, because the control valve, when it's being used, isn't going to go from fully open to fully closed. It's meant to control the flow, and you don't see large actuations from the stem. You see oscillations. And so this ISO is meant to cover all sorts of applications, from cryogenic up to really hot applications where only a graphite packing might be able to be used. So when you have the different temperature classes, at 400 degrees C, we won't be able to use a PTFE packing. But at 200 degrees C, we can use a PTFE packing. So what these temperature classes are really doing are not only mimicking different applications, but really limiting your packing selection as well.
So 400 degrees C is really high. That's getting close to the ignition temperature of methane. Are there any concerns with that?
There are some concerns with that. You wouldn't want to test methane at 400 degrees C. You're really approaching the ignition temperature of methane and cutting into your safety factor quite substantially. So I know here at our test lab, we won't be testing any methane at 400 degrees C. It's just it's a very large safety concern for us. Again, we have multiple leak detection methods. We have the vacuum method, which would only be used for helium. We have the bagging method, again, only for helium. And then the sniffing method, which would be your EPA method 21, which can be used for either helium or methane, depending on the capabilities of your measurement equipment. And what the vacuum method is, it's essentially you need a very large canister that's vacuum tight to be able to pull a vacuum through with your test equipment. That was found to be extremely difficult to achieve and extremely costly when testing multiple valves. Essentially, you would need a new test rig designed per valve every time a valve was tested. So what they came out with was the bagging method, and essentially this is either a foil or a plastic wrap around the stuffing box area. So essentially you have your yoke extending up above the stuffing box, and that will be bagged with either a foil or a plastic wrap. And a port is actually made on each side, and on one side you'll have a long tube, on the other side you'll have your leak detection equipment. And this ensures a steady flow of air through the bag. And again, you have your EPA method 21, which is going to be your EPA accepted method. the only one that really is accepted for methane, and probably the easiest method out of all three. And retorques are allowed in this test. So per endurance class, whether it be a control valve or a block valve, each has 3 endurance classes. You have 1 retorque in each class. So if you're going to cycle class CC2, you're allowed 1 retorque in class CC1 and a following retorque in class CC2. But you cannot retorque more than once within each endurance class. And each adjustment has to be recorded in the valve marking and the test report. And this will be marked as an SSA, which is a stem seal adjustment. And one interesting thing about this test is the way that the valves are marked. And this is really supposed to be a very quick, easy summary that's marked on the valve so you know what the capabilities of this valve is. So down here we have ISO FE BH. So that's leakage class BH. So that was tested in helium to class B. CO1. So we're looking at an on-off valve. The CO is for on-off. Class 1, so 205 cycles. SSA 1, so you have 1 stem seal adjustment during your endurance class. This was tested up to 200 degrees C at the rated pressure for a 300-pound valve to ISO standard 15848-1. But if you go to the third example, we have ISO FE-CH, so again helium to class CH, endurance class for an on-off valve CO3, 3 stem seal adjustments up to 400 degrees Celsius. But what we see here is a 30-20 pressure rating. So this means the valve was tested to 30 bar at ambient and 20 bar at the elevated temperature. And what you see with this is that, so if you have a 1,500-pound valve, you can say your 1,500-pound valve was actually tested to ISO. But what you have to look at is the marking. And if the marking doesn't say 1,500 or CL 1,500, but says something like this 30-20, the valve wasn't actually tested to the rated pressures of a 1,500-pound valve. It was tested to 30 bar and 20 bar. So technically it was a 1,500-pound valve that was tested, but it wasn't tested to the intended pressure ratings of that valve. So this is something that you would have to pay close attention to if you have any doubts that a given valve may or may not been able to pass the test that it's stated to pass.
All right, so yeah, I can see the ISO is written a lot more broadly, so there's also a little bit more room for trying to squeeze things by and say that they're ISO rated.
Correct.
All right. So TA Luft. It's the Technische Anleitung zur Reinhaltung der Luft. I hope my high school German teacher was proud of that pronunciation. Which is the technical instructions on air quality control. Michelle, who's a native German speaker, says maybe. This is essentially the Clean Air Act of Germany. So this is a German standard. The people who are going to use this are basically people in Germany. But that standard is actually extremely vague. Like the Clean Air Act, it's very long. It covers a lot of stuff, and there's really just one paragraph on valves and specifically on stem leakage. So really what they go for is they use this other testing method that's VDI 2440. So medium is helium, the pressure is the pressure class of the valve, the temperature is the max operating temperature of the valve. So far you can see this is actually closer to ISO than it would be to an API standard. Mechanical cycles are representative. Basically, kind of like ISO, this is going to be an agreement between an end user and a manufacturer and whoever's doing the testing to figure out, based on what they're going to use the valve for, what they would consider kind of the lifetime of a valve, how many actuations they're comfortable testing with. Collection method is vacuum, so expensive and difficult, but It's kind of the most rigorous. And the acceptable leakage is that volumetric leakage rate that you can only measure using helium with a vacuum or with a bagging method. And there's one retorque allowed. The whole point of TA Lift and kind of how they came up with these standards is that the actual technical instructions on air quality control specify that you should be using best available technology or equivalent. So, which is really metal bellows seals for valves, but those are expensive. You can't use them on every valve. So this was kind of used as saying, well, if it can meet this standard with a graphite or a Teflon packing, then it's basically as good as a bellows seal. And I believe that's everything. So I still have some questions. But you guys can, if you guys can think of anything, feel free to type it in there. And if you have any burning questions afterwards, you can feel free to email us, and we'll get back to you.
Yeah, there was a lot to cover right here, and so we didn't get into this very specific details for a lot of these tests. But if you guys have any questions, just type them in now, or you can contact us later.
Oh, Ron's typing. So he's getting that question out. One of the things that I'm always interested in is when valves fail these tests, especially for something like 624, where it shouldn't be the packing that's failing. What kind of things can cause a valve to fail? What part of the design?
Well, API 624 is unique in that the packing has already passed the test, so we tend to not look there immediately. Some other things that might cause a valve to fail are stem condition, if there's any pitting or scoring or scratches on the stem, if the hardness of the stem, the acne threads of the stem, if they're too large, cause a problem. Any installation procedure misstep, if something fell into the stuffing box or the sealing area as it was being installed. The bonnet seals, of course, there's other areas outside of the stuffing box on the packing related area that could fail. Flanges, bolts and torques. If the bolts are being reused, a lot of times you have a much lower torque value than you would with a brand new bolt. There's a lot of reasons why a valve might fail outside of just the packing.
Yeah. So some of those can be brought into what you would do in the field, which is things like use new bolts, lubricate your bolts. One interesting things you said about the stem and the threads on the stem is that when manufacturers they assemble these valves, usually they drop the entire cartridge of all of your sealing rings in at once, and then they push the stem up through. This is something these guys actually taught me. And if your stem threads are the same OD as your stem, you're likely going to rip up your packing as you do that. So
for sure, we've even seen some that were larger than the OD of the stem.
Yeah.
Tears up the packing.
That makes no sense. So Ron asked, does TA Lift use a valve or a rig? And Greg, you already responded to him. You want to talk a little bit about that?
So the TA Lift test that we utilize in our the version of, because it is quite a vague description of a test, so you might see some variations depending on the test facility. But we use a rig that was specifically designed for the TA Lift test.
So he asked you, they have a specific valve test also, i.e., 622 versus the 624. I think again that's the whole vagary of the way it's written. Mm-hmm. That you might want, some people might require that the valve is tested, to that VDI 2440. sometimes you just want to use a packing that works for it. Correct me if I'm wrong, of course.
Yeah.
Again, it's a very vague test, and sometimes the interpretations of it are different. So we don't utilize a valve specific test procedure here.
All right. Ron asked another great question, which is why do vacuum do that? Well, we discussed why they use the volumetric instead of the ppm. He asked if there is a conversion between the two.
There is not a hard conversion factor. There's no number you can multiply the results of a vacuum method and convert it to ppm. There has been multiple tests over the years trying to correlate these two values, and nobody has been able to really nail down an actual conversion factor. It's just they're too different. There might be some slight correlation. I mean, obviously, if one's leaking heavily, the other one you can be expected to be leaking heavily, but the actual values of the actual measurement you can't convert.
Yeah, so ISO basically had to draw a line in the sand with they have the two leakage classes, and they kind of find what's low leakage in helium volumetrically and what's low leakage in methane using sniffing and using ppm. But they're also sealing the two different media is different. Methane is a much larger molecule, so helium's going to leak more anyway. So even if there was a conversion between units, the fact that you're using a different media makes everything a lot more complicated. All right, so what about if valves change? So if the valve manufacturer changes some part of their valve, where's the barrier when they might have to retest it?
So any change to the sealing area generally requires a retest. Every standard is specific to itself, so it's really important to read and understand the standard that you are working with. But yes, any change to the sealing area, any change to the packing usually requires a retest. A lot of times a material change, if you're going from one class of material to another class in ASME 16.35, or is it 2.4? 3.5. Anyway, if you're going to a different material class, usually you'd have to retest the valve because all the materials have different pressure ratings. Basically anything functionally on the valve that changes requires a retorque.
Ron asks, what about change to gland load?
In what sense? So we do find when we test over time we lose gland load, and that's why we retorque in order to reapply it. If they are stating that they needed one gland load and now they're saying we need a new gland load in order to seal, then yeah, that would be a change to the procedure that would require retesting to know that the valve will in fact seal at that gland load.
All right. So
Paul has a good question here. Does live loading come into play in testing? The intent of most of these tests are for a valve to be essentially pulled off the shelf and tested. If an API 624 test, the valve would typically have live loading. The valve may be tested with live loading. What you run into issues with is that typically the test is going to state that the valve is live loaded, which would require the valve to always be live loaded to be certified to API 624. Most of these valves are commodity items, so a lot of these manufacturers aren't looking to invest in live loading. It's quite expensive to get your packing set to seal, especially for these packing sets that don't necessarily need live loading. But when we're talking about ISO, is you have a control valve. These aren't necessarily commodity valves. So you have a lot of these manufacturers are willing to put in a little bit more money to get the performance that they're looking for. So a lot of these valves will be live loaded.
yeah, and for anybody, if you're wondering what live loading is when you're actually basically using Belleville springs, which are disc springs. They're basically concave and convex washers that you put together, and you're using that to put the load on the packing. So that'll help it withstand, if the packing consolidates at all, so it loses a little mass, or if it extrudes a little bit, it's going to help to keep that load on there. It'll also help if there's any changes due to thermal cycling, as things are growing and shrinking.
But what I think to better answer Paul's question, it comes down to the customer, or the manufacturer. If they're requesting that no live loading be used, live loading wouldn't be used. If a customer is willing to have live loading as an option to have the best performance out there, we certainly do live loading, especially when we're testing control valves using PTFE in high cycling applications. It's most certainly going to be live loaded, but for a block valve, typically not.
And the key is that your test conditions are always documented. If you use live loading in a test, you would want to document in the certification that that valve was tested with live loading, and that the same test results might not apply if that valve is not live loaded in the future.
All right, I have another question, which is, say I'm a manufacturer, I send you guys a valve, you test it. Do I want you to send it back to me so I can go and put it in the field and get my money's worth out of making that valve?
Typically not. Well, a lot of these tests are really pushing the life cycle of a valve. You're going to have damage. A lot of times you'll have a valve that barely squeaks by testing. With 624, 310 cycles, the valve might be close to falling apart by the end. It might pass, but a lot of the components are at the end of their life cycle, and typically you don't want to put that valve back into service.
All right, so it's these life cycle tests.
Yes.
Yeah.
So valves can't do 2 life cycles by definition of life cycle.
They're not prisoners.
Yeah. All right, so I think that's pretty clear for me.